into this talk today, having to do with David standing before Goliath. And David had the gall, as a young teenager, to stand up to Goliath in front of the whole country of Israel and the nations there, and to defy him and take him on, a giant that was twice as tall as he was. And he ended up prevailing. Well, we didn't have any confidence that we were going to prevail, but we had trust that the Lord would provide, and we prayed in a very special way that he would do so. And we were just gratified when the Lord did provide, and provided answers for us through this project. We prepared a number of samples that we sent out to laboratories, and I must say at this point that this project raised $1.25 million for this work over the 8 years. That was another thing that we had no confidence in. In the past, probably the largest amount of money that we'd ever raised to do research was something on the order of $10,000 or $20,000. Even to think about raising $1 million, which is what we expected this project would cost, was presumptuous, we thought. But yet we depended upon the Lord to provide it, and he did. He provided the money exactly when we needed it, in the amount that we needed as we went along. And we came through the whole project with everything completely covered. Just amazing. One of the things that we did, though, in preparing our samples, rather than having a laboratory, which would have cost more money than even the $1.25 million to do, and having technicians that were constantly prepared to do all kinds of analyses, we didn't feel that that was a good use of the Lord's money, to have a lab that would do a few samples and then never be used again. So we decided that we were going to send our samples off to commercial laboratories, university laboratories, and government laboratories, and pay a fee to have the work done. There was also another reason for doing that, and that was that if we had done it in our own lab, one of the criticisms that would have come would have been that we doctored the results. So we wanted it done in a laboratory that had a good, solid foundation, had a reputation, and could defend the measurements. So what we did was we collected the samples in the field, we prepared them in our laboratory where we ground them up like this, and we then sent them to the laboratories, got the results back, and then interpreted them, and then write the report. There was all kinds of work, special work that had to be done, even in preparing the samples. We had to break the rocks up, which doesn't take a lot of smarts, just a big sledgehammer. Have you ever seen a mortar and pestle made out of iron? That's how you break up rocks. It's like what doctors use to crunch up pills and stuff. But here you have to have larger equipment and really heavy stuff. And it takes a strong back and a weak mind to do that. We all participated to a certain degree. I'm not even suggesting that Bill Hoche has a weak mind. Don't go there. But he was very helpful in doing the sample preparation. But it took a lot more than that. In order to separate the various grains and minerals in these rocks, we had to use special techniques of flotation. First of all, you run them through sieves at different density of mesh, and separate them out that way. And then you also have to put them into what are called heavy liquids, so that the liquid is intermediate between, say, two kinds of minerals, so that certain minerals are more dense than the liquid and fall to the bottom. Other minerals are less dense and therefore float to the top, and then you separate them. You can also separate them if they happen to be magnetic by using magnets. One of the most frustrating things that we had to do was to do it under a microscope with a pair of tweezers and separating out individual little grains of crystals. So there's a lot of work involved in this process. These are some of the stuff from the labs. Okay, now what I'm going to do is give you an overview of the results of the R.A.T.E project. And the first one I'm going to talk about is Dr. Russell Humphreys, his work on the diffusion of helium. Now, helium is also a daughter product, for example, from the decay of uranium into lead. When uranium decays into lead, it not only produces lead, but it also produces helium at the same time. The alpha particles that are produced are actually the nucleus of a helium atom. So when it then collects a couple of electrons, it is truly a helium atom. This helium then is embedded in the rock with the lead, but it's a gas and diffuses out through the crystal structure, the crystal lattice, out in the rock. We had already known from some work that Dr. Robert Gentry had done that many of these rocks that we were going to be studying still had a lot of helium in them. Now, you know that if you've ever bought a balloon for your child, or maybe you're young enough you've had your parents buy you a balloon, You know that if you tie it to the bedpost and you wake up the next morning, the balloon is kind of deflated and falling down toward the floor. It's because the helium is such a small atom that it can diffuse through the actual molecules of the rubber in the balloon. It does the same thing in rocks, not as fast as going through the balloon, but at a very fast rate compared to other type gases. And if, in fact, the rocks that we were studying, which many of them were conventionally dated to be 1.5 billion years old, based upon the amount of uranium and lead that was there and the measured or known rate of radioactive decay of uranium into lead, there should be no helium left. It should have all diffused out. And yet there was a lot of this helium still left in the rocks. Now, many of the rocks that we dealt with had embedded in them zircons. These are little crystals of zirconium silicate. And they are very small. They're on the order of 100 microns in length or less. 100 microns is about the diameter of the hair on your head. So they're very, very small. You can only see them under a microscope. But in these zircons is where the uranium is located, typically in a radioactive sample, a radioactive rock, and particularly in granites. We were looking primarily in granites, in which there was zircons embedded and other material called biotite. But these zircons contained the uranium, and the decay was going on inside these zircons, producing the lead, producing the helium, which then diffused out of the zircons into the rest of the rock and out into the atmosphere. These zircons are very interesting because they have a very high melting point, such that they actually will be drawn into the magma that's in a volcano, shot out the top of a volcano, and then re-solidified. The magma will re-solidify as solid rock, and those zircons have never been melted. They can actually be processed through volcanoes without changing them greatly. Here's what a number of zircons would look like. There you can see the 100 microns. Some of them are almost 100 microns long. Here's a photomicrograph of one in great space. This actually the smaller dimension, or the width of that, is about 20 microns. So it's on the order of about 50 or 60 microns long, this particular one. And it has these little faces on it, which makes it very interesting to work with. As I said, as the uranium decays, it produces not only lead. It starts off as, say, uranium-238 and ends up as lead-206 or lead-207. And in the process, it goes through a whole decay chain. And in various places in the decay chain, there's alpha decay that occurs, and it produces, for each one of those alpha decays, it produces a helium atom. So each uranium atom, by the time it ends up with a lead atom, there's been 8 helium atoms produced on the way. Okay, now this is a uranium atom with a bunch of electrons around it, and it's going to be exploding and sending out alpha particles, shooting out into space here. Here's an alpha particle made up of 2 neutrons and 2 protons. Let me do that one again. As the alpha particles come out, they shoot out in all different directions, and the alpha particles, as they slow down in the crystal, they collect electrons and then become helium atoms. Now, these are all embedded inside the rock, and the helium, as it is trying to diffuse out of the zircon, then can diffuse out of the rocks. And it looks kind of like this. Here's all this helium coming out of the rocks at the microscopic scale. Oh, nothing is showing here. Did the other one show? No. You didn't say anything and you said, oh my. Uh-oh. Oh, sorry about that. I don't know whether I'm going to be able to get this to work or not. Well, it worked on my projectors before. Mike, you got any suggestions? Mike Riddle? Uh-oh, I'm in trouble. Well, let me try it. Do an F5, you mean? Let's see if that'll work. No, that's too bad. Nope, that didn't do it. Nuts. Well, nuts. Well, that's going to be one of my special features. Yeah, that's right. Well, okay. We'll keep going here. Sorry about that. For those of you that just got to see the animations, I'll have to show you privately, I guess.